Are we recording?
Yes, we are. That's what it says.
Okay. It's a typical opening dialogue. It's never terribly inspiring in these things. That's live theatre for you. You notice that live theatre makes really terrible television. But so it goes. So so far this semester, we've been looking at how logical connectives work and how to prove stuff using them in a way that is kind of divorced from reality. I mean, it's very difficult to invest emotionally in P and Q. You know, oh, good. Q's true today. That's cheered me up a lot. So I'm hoping that by the end of this lecture, we will have arrived with logic actually being about stuff. You know, we might actually prove interesting things about programs that we might care about. I should also warn you, if you didn't clock it from Mattermost, I should share my screen on Zoom, shouldn't I? So share, and I think I will just share the screen because I've quit my email client. And now all I have to do is persuade Zoom to stay out of the way. What's the hide floating meeting controls? Okay. So if by any chance you have your own offline installation of Ask, you will need to update from the repository because I spent yesterday tinkering, obviously. But you know, Ask is a test on deployment software system, you know, thrown into use immediately after being implemented. You know, it's this is not how to do software engineering properly. Sorry, folks. I'm just a dangerous bastard. And so one of the things I did yesterday was to equip Ask with a notion of equality for propositions. So far when we've been proving equations, we've been proving equations about data. You know, equations that say, oh, the result of this computation is the same as the result of that computation. And but we are going to extend the notion of equality to propositions in what I hope is an appropriate way. That's to say, two propositions are equal if they're logically equivalent, if each of them implies the other. So here's the rule that enables you to prove an equation. I'm going to use De Morgan's laws as an example. You say by equivalence, and you get two subgoals, which are hopefully unsurprisingly, given the left-hand side, prove the right-hand side, and given the right-hand side, prove the left-hand side. Does that seem fair enough? Okay, so okay, let's do it. Let's prove De Morgan's laws. So this one says if neither is true, then they're both false, which I hope seems plausible. Let's see what happens. Right, I want to prove not A and not B. I think I better prove them separately. So by and introduction. And now I have to prove not A. So if I do that by not introduction, and here I'll also do by not introduction, then I will be handed, respectively, a proof of A and a proof of B. And I knew that was going to happen. I could tell that, the way this is going to work is that I get my hands on a hypothetical proof of A, and then I know that neither A nor B is true. So fine. I'm now in a position to go from what my given. Remember that when you from a not, right, anything that's negated that you've been given entitles you to say, I don't like my current situation. I'd rather prove this, right? So I don't like having to prove false. I'd rather prove A or B. And that's quite a sensible thing to want to prove, given that I know I've got a plan, right? So you can see in this sub-goal, I've got a handy A. So I think I'm going to go left. Sorry? Yeah. And in this sub-goal, I think I will go right. And funnily enough, we're done on that side. Now, how about the other side? It's whenever you're given some sort of and, it's always a free hit just to split it apart. So that's just saying split the and up. Now we've given the two things separately. So we know we can disprove A and we know we can disprove B. So let's prove neither A nor B. We're being asked for a not, so we'll do not introduction. And that gives us A or B. So whichever of those two happens to be the case, we're ready to kill it. So we go from A or B, copy, paste. And there we are. We've been given A. We need to prove false. So let's go from not A and here from not B. Bam. All right. I'm not sure whether it makes sense for me and Fred to take turns today. What do you think, Fred?
Maybe we tinker a little bit in the break and see if it works.
Yeah. If I had the means to send sound, I mean, from the computer out the PA, it would be a whole different story. But I don't think I do.
Yeah, let's not do it now, I think.
Okay. Right. So we've shown that if neither is true, then they're both false, or that's the same as both being false. Now let's show that that if the pair of them together aren't true, that's because one of them has to be false. And there's something to be seen here. Right. Because on one side, we just know that they aren't both true. But is that enough information to tell us which is false? We kind of, in principle, know one of them's got to be, but in practice, can we figure out how? You should guess what's going to come up on this one. Anyway, same deal, by equivalence. And now I've got two branches. I'm going to take the second one first. So you can see here, I'm given that that either not A or not B is the case. So I think it'd be pretty sensible to find out which. I mean, actually, nah. It's always I'm just delaying the moment where I split the proof into two by just doing not introduction already. Right, and now I've been given A and B, I'll just take that, thanks, and split that in two. And now I'll find out which case I'm in. So that was two free hits. I could have done this split earlier and then I'd had to do the same job twice. Right, okay. I think we're going to win. Okay, so that was nice. Right. Uh, so, we're trying to prove not A or not B. We've got some information which might be useful if we happen to know both A and B. Now, the thing is, if I choose to go left or to go right at this point, I will be handed a hypothetical. If I go left, let's do it actually. Why not? If I go left, then I will be handed a hypothetical proof of A. But I have to prove false. And the only way I can get out of this is to make use of not A and B, and I don't have a B. So I made my commitment too early. And it would be the same situation if I went right, I would be handed a B and I'd have no chance of getting an A. So I think we know what we're going to do. We need to go into sheer bank robbery mode. Let's start again. And rob some banks. Okay. So this is good. I think I'll go from okay, and now uh uh you might think nothing's changed, but really something terribly important has changed, which is that my getaway car is gassed up and ready to go. Now when I go left, I get handed a proof of A. And what do? I grab it and run away. This time I'll go right. Oh, goodness me. Now I have an A and a B. So yeah, that's finally I'm in the right place to do that. When I go by and introduction, I'm going to win. So once again, by contradiction, lets you do stuff that makes sense from the point of view of kind of an omniscient being who knows everything, who can decide everything, for whom the world works in a Boolean way. It just doesn't correspond to the computational reality we live in. And yes, we've been teaching this to the fourth years, where we actually, where this is sort of deeply noticeable in the stuff that we do with them. Okay, so that's a couple of equivalences, and you'll notice it's one direction of one of the De Morgan rules, the one that says, here's some negative information, and here's an actual bit of information, right? It's not an actual bit of information. It's a magic bit. Okay. What time is it? It's plenty of time to muck about a bit more with the same stuff. So just to get used to this idea a little bit more, if you are in a Boolean world, then A implies B is the same thing as either A is false or B is true. That's to say, the implication either holds because the premise is false, in which case it's what we call vacuously satisfied, or because the conclusion's true anyway. So let's prove that. And fine. This direction, same situation. So here's the trick. Remember, if you're looking at this disjunction, this or, and you think, oh, I can't possibly know which way to turn, that's a very big clue that if you're being asked for a magic bit, and you should take the magic pill. Right. Okay. So I do this. And you know what's going to happen. Right. So now, what am I going to do? What's my best strategy for getting anything out of any of this stuff? I've got an A implies B. So I would really like to be given an A. How do I get my A? Well, I'm not going to go right. That won't get me an A, but I will go left. Then I'll be asked to prove not A, and I'll do not introduction, and that'll give me an A. Excellent. Because now I do this trick. You're going to get right. Now, now that I've got an A, and an A implies B, do you know, just for a change, I think I'll go right. You're learning how to play this game. Yes. Right. Okay. Hopefully this way around is slightly easier. We do because this time, instead of manufacturing a magic bit, we're being given an actual bit. So that should make life easier. So we did implication introduction because that's a free hit. And now we've got no choice but to find out which of these situations is the case. And you can see we only get one sub-goal because B implies, given B, prove B is trivial. So ask doesn't even bother us with it. And now I've got A and not A. So I'd rather prove A. Okay. So that's a fine example of an equivalence which holds in a Boolean world, but really does require contradiction because this OR is a magic, you know, we're figuring it out by magic. Okay, so one more example of this, and then we'll do something else. I should draw your attention to, well, okay, so you might remember that we also use this arrow. This arrow means implication, implies in a proposition. But we also use it to make function types. So if I don't tell ask what's going on, ask doesn't know whether this thing is an equation, is supposed to be an equation between types or between propositions. I mean, it could figure it out from the knots if it really thought about it, but ask's just too stupid to figure that out. So what I've had to do to state this goal is to slap a type annotation somewhere. So prop is the type of propositions. So all I'm saying is, hey, ask, this equation is between two propositions. The thing on the left-hand side is a proposition. And that's, just deals with ask's stupidity by being explicit with it. So this double colon prop just means this thing is a proposition, but it's still A implies B. So let's go by equivalence. Right. So what we're saying is if A, then B is the same as if not B, then not A. So that's kind of backwards reasoning. Okay, so we've been given A implies B, and we are asked to prove this thing. And again, there's some no-brainer moves. We can do implication introduction, so we will. We can do not introduction, so we will. And now we have to prove false. Well, how can I prove false? I have not B, but do you think I can get my hands on a B? Yeah, I think so. So I say from not B, and then from A implies B. And we're done. Okay. So that's a nice start, but the other direction is going to be slightly more entertaining. Okay, I'm going to go by implication introduction. Right. Can you see anything that's actually going to give me a B? We know some consequences of B being false, yeah? Right, but that's what we're trying to prove. So we don't have that in our pocket. That's where we're going. Right. So the problem here is that I've got no B's on the right of an arrow or anything like that. There's nothing I can shove stuff into and get a B out. Which means I'm going to have to do some magic. Not B doesn't count. Well, not B is how we're going to win, but the trouble is that it's negative information about B. So there's nothing that will actually spit out a B. So we have to arrange not to need a B. Okay, so I've got slightly more chance now. I've been given not B, and I also know A. So now I'm in good shape, I think. Let's go from not B implies not A. Because I certainly got not B, so now I can get my hands on not A. And I'd quite like to get my hands on not A, given that I already have my hands on A. I can blow up the world. Right. Given not A, prove false. From not A. Bam. So there we are. A bunch of fairly famous logical equivalences, some of which hide the fact that there's some kind of magic figuring out of bits that that you only get by kind of being omniscient. But yeah, that's cool. It's just gone 30:30, and I hope we have done that to death. I hope you're getting the message, or that some sense of when to reach for contradiction as a big stick. It's you know, when essentially you're being asked for information that you have no equipment to compute. That's when you go for contradiction. Okay. So I want to change tack just now, and show you something new. Because so far, we've been, just leave a bit of a gap there. So far, we've been, maybe I will just leave a little bit more of a gap. We've been working with propositions assembled from logical connectives, but they at the base case, we've always had these propositional variables, which are abstract. And so that means we've been learning general reasoning techniques, but it hasn't been about anything. So let's give ourselves some stuff for reasoning to be about. So the thing is that ask lets you invent new kinds of proposition. So here, I've got a very simple data type called throw, which gives you, which has just got 3 values in it: stone, paper, and scissors, which are the 3 things you can throw your hand into in the classic randomness game. And then we invent a new proposition. Actually, we call this a relation. So a relation is a proposition which has some parameters. That's often, but not always, 2. So here we're defining a relation, which I'm going to pronounce beats. And this is an infix thing, and it relates 2 throws. Okay, so a thing that I didn't show you last semester is that ask allows you to create infix operators made of symbols. So when you see symbols, not letters, it's an infix operator, takes our inputs on either side. So this says, I mean, it's that when you put greater than, or beats between 2 throws, you form a proposition. And so that's one thing. I've invented a new kind of proposition. This beats that for 2 throws. And then I have to say what the rules are for establishing when this beats that. So here, instead of, I write it like we're in the middle of doing a proof. I show what the moves you can make are. So if you're trying to prove paper beats stone, then you can do that by wrapping. Paper wraps stone. scissors, cut paper, stone, blunt, scissors. So I'm inventing 3 new rules that we didn't have before that explain how to do proofs in this world of stone, paper, scissors. Okay? So we'll see how that boils down. So here are some examples. Actually, now I will just
Connor, do you want to point out the common syntax mistake that these things have to start with an uppercase letter?
Okay, yeah, sure. Thanks, Fred. Things like types must start with an uppercase letter. Data constructors must start with an uppercase letter, and the names of rules must start with an uppercase letter. The rule of thumb here, this is stolen from Haskell, is that a thing which begins with an uppercase letter is itself. It doesn't stand for anything else. It's not a variable. A thing which starts with a lowercase letter is either a variable, it stands for something else one way or another, yeah? I mean, it's the classic game where 2 players simultaneously make a throw without knowing what the other one's going to do. And then the outcome of the game follows these rules. Paper, rat, stone, scissors, cut, paper, stone, blunt, scissors.
Okay. Maybe you could play around with someone.
Let's see. Maybe I don't think we can see you well enough for me to play around with a round of Zoom.
Or you could play with someone in the audience.
Maybe I could. Or even better, I can indulge in blatant copyright theft. If only I can find, yes. Maybe Zoom is going to prevent me from.
Paper, wrap, stone.
Hair, stone, blunt, scissors.
Scissors cuts paper. But suppose we were 2 computers controlling 2 great battlefields, eh? Each one working perfectly logically to outmaneuver the other. Well, you're robots, you try it. We are perfect. Try it. Go on.
Absolutely typical of Tom Baker to start something important that's visual and then just get in the way of the camera. You know? Anyway, that's classic Doctor Who occurrence of this game, which is where I mean, it's an ancient thing that Doctor Who was ripping off, much like everything that Doctor Who ever does. Yeah, that's I remember seeing that when I was little. I must have been 6 when that was on television. Anyway, let's prove another equivalence. So here we're saying the statement paper beats X is equivalent to the statement X is stone. That's to say, there's exactly one thing that paper beats, And that thing is stone. So, okay, we go by equivalence. All right. So let's do the second one first. When you are given an equation where one side of it is a variable, that equation is not automatically a definition. So if I say by wrapping, wrapping doesn't prove paper beats X. But what I can say is from X equals stone. What good does it do me to know that X is stone? Well, guess what? It means the goal, I can replace X by stone in the goal. So you can do that when one side of the equation is a variable. Then, so if you say from variable equals thing, then thing will be substituted for variable. Here, stone was substituted for X, and now we can proceed by wrapping. Okay. Now, how about the other way around? Well, here, the point is that when we defined the beats relation, we gave the 3 rules by which one throw beats another. And those are the only ways one throw can beat another. So not only are we saying something positive, these are the way one throw beats another, we are also saying, and that's your lot. So correspondingly, we are entitled to think backwards. We are allowed to do a bit of detective work. If this is true, if we're given that paper beats X, how could that possibly have been proven? If you look at the 3 rules, which of the 3 rules could possibly have given us that paper beats X? There are only 3 suspects, and 2 of them have an alibi. So what do we do? Well, of course, it's yet again, it's a from. So in ask, from is always make use of this to solve my problem. Okay? So I say from paper beats X. And that actually does it. It's a bit too it's a bit too subtle, actually. Because what it actually figures out there is that it can't have been cutting, it can't have been blunting, it must have been wrapping. So X must have been stone. Job done. That making sense? It's a bit slightly too much ask magic, but you can see what's going on is that we get a kind of partial fit. So what happens when you do from on a relation is that it looks for all the things that are a partial fit, and it fixes up the discrepancies with equations. So if things don't fit, like, you know, cutting didn't work because paper isn't scissors. Blunting didn't work because paper isn't stone. Wrapping worked because paper is paper, and that means X must have been stone, is the reasoning that's going on here. So it works quite hard on your behalf. All right. So actually, let's do this one. So in honor of the Movellan robots who both kept coming up with scissors, let's show that X never beats X for any old X. So you have to prove not of something. So we'll do not introduction. Okay. And now we have that x beats x. So let's ask how that could possibly have happened. Ask is not super clever about this, but let's see. We say from x beats x, and we get that all three rules fit if you fix them up with some equations. But if you look at the equations, they're a bit suspicious. You got what we're saying here is it could have been wrapping, in which case paper is stone. It could have been cutting, in which case scissors is paper. It could have been blunting, in which case stone is scissors. And we are entitled to say, hang on a moment. Paper isn't stone, right? So if you see an equation, if you're given an equation between two things that are blatantly different, then you can just from it straight away and you will win. But scissors isn't paper. But stone isn't scissors. Okay, so that was a nice little bit of reasoning by cases and getting rid of equations that are blatantly untrue. Okay, let's do one more before halftime. Namely, for any A, B, and C, if A beats B and B beats C, that nearly came out as BBC, then C beats A. So do we believe this about this system? Right. And there's a little bit of tradecraft involved in this thing. So once we arrive in relation land, you need to sometimes think a little bit about when to make moves. So going to start with, because it's an implication, just in case it's tricky to read, I'll just put some extra spaces in. Okay. And now we've been given that A beats B. Right. I could do implication introduction here, and it would not be fatal to do so. But I know I'm going to have to do from on A beats B sooner or later. And if I do it sooner rather than later, I'll get a little bit more specialization in each of the cases. So I say from A beats B, and you can see that I get three cases because A beats B could have been any of the three rules, but you see that it substitutes out the equations in the goal. So in this case, A and B have been substituted out in the goal, and that's useful information. So the substitution doesn't happen in any givens, only in the goal, which is why it was a good move to put off doing implication introduction until after those substitutions had happened. Okay? So now I do by implication introduction. And now I've been given stone beats C. And this time, I only get one case. We figure out that C must have been scissors. So I need to prove that scissors beats paper, and that's true by cutting. Okay. By implication introduction again. And then from paper beats C. And that means C must have been stone. In which case, the goal is true by blunting. And then same again. From scissors beats C. C has to be paper. Paper beats stone by wrapping. Okay. So there we are. That's a nice little bit of inventing like a little system which has its own particular rules and reasoning forwards towards conclusions, invoking those rules by wrapping, by blunting, by cutting, but also doing the detective work to ask if you give me something beats something assumption, how could it possibly have been true? Okay, this looks like it's sort of pretty much 6 minutes to, so let's take a short break. Probably back at 4 past. All right. I will stop sharing for a moment.
Yeah, should we try and see if we can get the audio working, or should we just continue like this?
Let me see if I can find anything that looks like it might be. I wonder if I switch to HDMI.
Yeah, I was about to ask, how are you connected?
I'm on USB-C.
Yeah, HDMI might work, right?
Half chance. So.
Are you now back on HDMI?
I am.
Can you hear me any better? No.
Actually, I can hear you, but the trouble is.
Yeah.
Now, I do wonder whether what I need to look at is settings, audio.
Yes, your computer audio.
If I do speakers, I wonder if this is the thing.
Well, let's see. I'll just gratuitously say something else so that we can see if it makes a difference.
Yeah, you are in the room, Fred.
Okay.
I might actually need to just tweak the volume down a touch.
I see.
Sure. Wildly loud, but it seems to be not letting me adjust the volume. Maybe
you could do it on the thing, right?
I'm trying to. I'm not seeing a bar moving or anything like that.
At the bottom of the screen, I think.
Technical controls. Yeah, I can see there's some. Okay. I'll try now.
Yep. Okay. Now is now.
Yeah.
And I'll keep talking just for a little bit longer, just in case.
Yeah. I think we're there.
Yeah.
All right, cool.
Okay. I guess I have to be ready to do something. Yeah.
Yes.
Maybe you start after the break just to
Uh-huh.
say where we're going.
Um, so this is Fred's in his office. Yeah, there's some plants and some maps. And there's a painting just out of shot.
Falling down.
Okay, cool. What's next anyway? Oh, yes. Aha.
Right. Let's take a short break.
Sure. Actually, yeah. I'll also take a short break. Hello again.
Hello.
Right, I stopped sharing, didn't I? I guess I should start again.
Yeah.
Okay. Okay, folks. Shall we kick off again? So before we do anything more substantial, let's get ourselves some useful equipment for actually exploiting equivalences, right? So far, the logical equivalences we've encountered in this lecture, we have been proving them rather than exploiting them. But we're going to need to do both real soon. So I hope it does seem reasonable to you that if you know A is equivalent to B, and you also know A, that you can deduce B. And likewise, if you know A is equivalent to B, and you also know B, then you can deduce A. You know, let's not be astonished by these things. Nonetheless, let's get on and prove them. So this is an implication. So free hit, do implication introduction, and then for another free hit, just split this pair apart. Okay. We are given A and we're asked to prove B, but we know an equation. And one side of it's a variable. So we can rewrite with it. I say from A equals B. And that turns out to have been a bad move. In fact, so here's the thing. The equation affects only the goal, and there's no A in the goal. There's a B in the goal. So what I should have done was from B equals A. So when you do this, it rewrites left to right. So it's replacing all the B's in the goal by A, and it is perfectly willing to check that. So remember that when ask is checking whether an equation is given, it tries it both ways round. So from B equals A is justified because I've been given A equals B. Okay? The other one's actually easier. Implication introduction from just splitting up the pair of things. And now here I've got an A in the goal, so I want to turn A's into B's, and we're done. So they're not exciting, you know, there's you're not, I hope, fainting with amazement that these things are provable, but you know, we're doing that because they're useful. Okay. So that's some kit that we will make use of. Right. So here, welcome back to the world of spuds and lemons. Here's a definition of the less than or equal relation. So this thing here is saying there's a new kind of proposition. It's formed by the constructor le, or less than or equals, and it is parameterized by two numbers. And then we give the rules for how to deduce when one number is less than or equal to another. And there are two rules which do this, and we have named them. The first rule, les, says that 0 is less than or equal to anything. That's you know, if your left hand has a lemon in it, then that's definitely less than whatever's in your right hand. Less than or equal to. And the other rule says if you've got two big numbers and you want to prove one is less than or equal to the other, then throw a spud away from each side and keep going. So to prove that successor of n is less than or equal to successor of m, then prove that n is less than or equal to m. So those are the two rules, and the only two rules for proving that one number is less than or equal to another one. If you're wondering why I have n on the left and m on the right, it's because n has 2 sticks and m has 3. Right. So I have a plan for a thing I want to do, but might want to warm up a bit to it first.
Could you do just an example that one is less than 3 or something like this?
Let's do 1 is less than or equal to 3. Prove successor of less than successor of 0, successor of successor of successor of 0. Okay. Right. And this is not going, you will not faint with amazement at this, right? When you've got some actual numbers, then you can pretty much see what rule to use, right? We're going to kick off by less. So we're proving 1 is less than or equal to 3, and we're told, yeah, fine, as long as you can show that 0 is less than or equal to 2. And then here, we're absolutely fine because 0 is less than or equal to anything. So you'll find in your tutorial assignment, do you remember back in semester 1, we had all of those formulae which represented functions, polynomials in one variable. So they're built from variable, natural number constants, addition and multiplication. So all of the polynomials you can build that way because of the nature of addition and multiplication, and because all the numerical constants are non-negative, all of those formulae have the property that if you put in a bigger number, you get out a bigger number, or at least as big anyway, yeah? So the fancy word, the Greek for if you put bigger things in, bigger things come out is monotonic. So all of the polynomials we built in our little language of formulae were monotonic, and your homework is to prove that. I've left a careful trail of breadcrumbs to get you there. You're going to have to prove something about adding. You're going to have to prove something about multiplication. And of course, to prove something about multiplication, you'll need to know something about adding, because multiplication is just doing adding over and over again. Okay. But I think we should prove some important things about less than or equal before we get on with the main deal. Actually, do you want to do this, Fred? Are you in a position to?
Yeah, I could try.
Can you, if I stop sharing and you share, can you prove that less than or equal is reflexive? Yeah. So.
Right, are you all seeing that? My screen?
I think we can see Fred's screen. Cool.
Right, so this is what you want me to prove? Yeah.
Yeah.
Okay, so let's see. So how would we do this? Well, problem is we don't know what x is, right? So we know that if x would be z, then we could use this rule because it says that z is less than anything. And if x is a successor, then we can make some progress with this rule, right? So I'm going to do a from x to, well, I guess, do I want to do it inductively x first?
I think you probably better.
Right, so in the 0 case, I'm going to be happy and be done, right? But in the successor case, I want to continue proving the same kind of thing. So I want to do this by induction on the x. So I'm just going to, just in case, say, okay, I want to do this by induction on x. Okay, and then my goal stays the same, but now I know that I can make use of the same fact on smaller x's, right? So at the moment, I don't know a smaller x, but let's see. Now I can do a from on x, and I get two cases. I get the 0 case, and I get the successor case, right? And in the successor case, I get these horrible variable names. I'm going to start by renaming these. So rather than x60, I'm going to call this x prime. And then, of course, you have to change all of the x60s. Okay, and then I try that again, just in case. Yeah, okay. So in the 0 case, then we said that we know how to prove that 0 is less than or equal to other things. That's what this rule says. I can just copy this in. Okay, and I ask is happy. And in the successor case, I also see that I have something that matches this second rule, right? So I could say by this rule, I should be able to make some progress. And indeed, so what's happening, well, this rule says that I get to know that the successor of x prime is less than or equal to the successor of x prime if only I can show that x prime is less than or equal to x prime. But that's exactly what I know by the induction hypothesis, right? So this is already proven. If I didn't have this inductively x, then I think Ask would not be happy here. Should we
Correct.
make that experiment very quickly? So
Actually, yeah, just comment out line 1 and move line 2 to the left.
Yeah.
Yes.
So you see that here, now I still have this sub goal. So I use this rule, which says that I can deduce that the successor is less than a successor if I peel off both of the successors and continue underneath. So I'm left with this goal, and that's exactly what the induction hypothesis gives me, right? But I have to ask for it with inductively x. So if I do that, can I do it like this? Yes.
Yeah.
But Ask is actually clever enough to see that this is given already, so I don't need that, right? But maybe it's good documentation. Okay, so that's how it works.
Okay, so the key bit of jargon here is it's Latin for a change rather than Greek, is to say that less than or equal is a reflexive relation. That means everything is related to itself. Right. And yeah, I guess shall I do the next one, or do you want to do trans as well?
Why don't you do it for a change?
Yeah. Okay. So
but remember to share your screen again.
Right, yes, true. So share, actually I'll just share the whole screen. Why don't I? Okay, you can stick reflexivity in Mattermost and then I can pick it up from there if I need it. Which I actually might. It's the rule for proving less than or equals when you've got two successors. Right. This is less than or equal for 0, and this is less than or equal for double successor. They're arbitrarily chosen names. I made these names up when I made these rules up. But I think they're reasonably mnemonic. Okay. Okay, so here's another important property of less than or equals. And you've seen this before in a number of situations. I'm saying that if L is less than or equal to N and N is less than or equal to M, then L is less than or equal to M. And I chose the letters in that order because count the sticks. And so this is Ellie is transitive. And again, I'm going to prove this inductively on, well, actually, it doesn't really matter what I prove it inductively on. Inductively on M, I think. M's going to be the biggest thing. Let's make sure it keeps getting smaller. Okay. So now we've got, it looks like nothing's changed, but we've got an induction hypothesis. As long as we make the big end a little bit smaller, we can do anything we like. Okay. So once again, I showed you this before with stone, paper, scissors. I'm going to take this very slowly. I'm going to do implication introduction, but just once. Here, I know some facts about L and N. And if I ask how they came to be true, I will learn something about L and N. Okay? And in particular, I would very much like to be in the situation where L is 0. That would be nice. Say from less than or equal Ln. So you can see this is yet another reason why we don't bake from into inductively. It's because sometimes you want to look at something which gets you a bit of extra juice. Okay. So first of all, I'm going to rename x67 to k and x68 to p, just to get the awful names out of my face. Okay, so in the 0 case, we've learned that L was 0, and that's excellent news. We can just race to the finish line on that one. We do implication introduction away. Again, the fact that n is less than or equal to m isn't terribly interesting. We're home. We know that we're trying to prove that 0 is less than or equal to something, and that's true by Les. Okay. But let's look at the step case. In the step case, the double successor case, we learned that L was a successor and that N was a successor. And because we delayed doing the implication introduction, we got a decent bit of substitution happening in the goal. So that's why I didn't do both implication introductions straight away. So now I'll do the second implication introduction. And now I've got some useful information. Namely, that in the middle, we've got a successor. So, how could that possibly be true? How could this assumption possibly have been given? We know that m is definitely bigger than 1. That's the point. So if we say from we will learn that m is also a successor. Okay. So that's nice. We've learned that L is 1 more than K, N is 1 more than P, and M is 1 more than Q. So that's all right. Maybe I should have chosen W instead of Q, because count the sticks. And V for P. You win some, you lose some. Okay, so we're in a situation where we've got 2 successors in our goal. So that means we can strip off the outer spuds using the double successor rule. And now we're in a situation. Now we've got to the stage where our goal has something that's 1 smaller than m. So we ought to be in a position to go inductively. So there's just a little bit of craft to show you. I grab the goal that I started with, and I replace L by K, N by P, N by P, M by Q, L by K, M by Q. Right. So this is an implication. So this groups to the right, remember? So using this fact, I will have to go in 2 steps because there are two assumptions that I need to feed it. So, okay, it accepts that the thing I'm froming is true. And that's because it's true inductively. That's because Q is smaller than M. Okay, but I still have to show. So it says, okay, and it also knows this thing because that's sitting around there. And then it's saying, well, okay, so you're entitled now to this conclusion. How does that help? Well, you just from it again, and it gets even shorter. Rom, not rom. And then it's saying, yes, okay, on the one hand, K less than or equal to Q is the goal. And on the other hand, yes, I do know that P is less than or equal to Q because, look, there it was. So we have managed to prove that less than or equal is reflexive and transitive. Right. There is a special name for relations which are reflexive and transitive. These things are called preorders. And semester 2s, you're going to get fed up with it, like corresponding to semester 1's monoids, you're going to get fed up with preorders. And you can see that there's a sort of slightly slightly monoidal flavor to preorders, right? Reflexivity is a way of saying there's a way of going nowhere. And transitivity is a way of saying if you can get there in 2 steps, you can get there in 1 step. So it's a way of plugging 2 less than or equals facts together to make 1, but they have to meet in the middle. So yeah, that's going to show up a lot. We've seen also, I mean, remember, we actually defined the identity function, and the composition function smells a lot similar. There's a lot going on. It's not a coincidence. Okay. What time is it? It's past. Okay, yeah, I should do. What should I do? Do you want to prove that less than or equals is a total preorder? That seem like a good job for you, Fred?
I could try. Yeah.
I will stop sharing. Right.
Okay. Right. So let's see if we have the same definition of total in mind. So one way to say that an order is total is to say that every 2 elements are related one way or another, right?
Yeah, one way or the other.
So I would like to show that either x is less than or equal to y, or y is less than or equal to x. And because it's less than or equal to, these are really the only 2 cases, right? I mean, if it was a so-called strict order where it's strict, x is strictly smaller than x, then there would be 3 cases. Either x is strictly smaller than y, x is equal to y, or y is strictly smaller than x, right? But in this case, we have included equality in the order itself, so there's only really these 2 cases. Whereas if x is actually equal to y, then both of these would in fact be true, right? Okay, so how would we prove this? Well, we have to look at x and y, because we can't say go left or go right before we know which one of them is actually smaller, right? And probably we're going to do some use the inductive hypothesis at some point. We want to say that, well, I can do it for smaller things, and that's enough. So I'm going to start by saying from inductively x.
It's not from, just inductively.
Yes, thank you. Okay, and there is absolutely no reason to kind of prefer x over y, right? So I suspect they also want to do inductively y.
No, you don't.
I don't. Okay, well,
yeah, I mean,
it doesn't cost me anything.
They're both going to get smaller, so it's not going to do you. It's not going to make. Yeah, generally speaking, doing inductively twice in the same construction causes ask to have a bit of a hissy fit. So,
okay, so it is going to cost me
you
something.
actively don't want to do a second inductively.
Right. Okay. So if I was just exploring things, then I would do it just in case, but I want not to run into kind of technical problems. So fine. Okay. It still remains the case though that I could just as well have done inductively y here, right?
Absolutely. Yeah. Either
the goal is very symmetric in x and y. Okay. So now I have access to the induction hypothesis whenever I have a smaller x. So let's look at what x actually is then, I suppose, right? So I'm going to say from x. And I get two cases. I will fix up this by replacing x93 with x prime. Send the task again to make sure I didn't mess up. Okay. So let's deal with the easy case first. So if x is 0, z, then my goal is to either prove that z is less than or equal to y, or that y is less than or equal to z, right? But that's good because we have, by construction, a rule that says that z is less than or equal to anything. So here I can go left, and then I have to prove this, and I just use the rule we designed for this. So that was easy. In this case, I don't know if I want to go left or right, right? Because again, I don't know what y is. So I think I better look at y. Because it could be that y is 0, in which case I want to go right. Could be that y is really big, in which case I want to go left, right? So I'll do a from on y. I again get two cases. Y is either 0 or a successor. If it's a successor, then I'm going to rename the variable to y prime. So of course, I'm only choosing y prime to remind myself that this is related to y somehow, but the name itself doesn't actually matter, right? Okay, so let's see. So I have these two cases, and let's look at the 0 case is usually the easier one. So let's look at this one first. Well, here again, we are in a good case, right? Where we are asked to prove something or something we know is just true, that 0 is less than something else. So I'm going to go right. And then I'm going to use the rule I have for showing that 0 is smaller than anything. Okay, and then I'm left with this case. And actually, this is a little bit annoying, right? So in both cases, I now have successors. So in both cases, I should be able to just peel off the successors and do a recursive call, right? But I still don't know which case I'm in, but I suppose I could. So I'm entitled to knowing this for smaller x because I didn't inductively x. So I should be able to do from x prime, y prime.
Prime all the things.
Because, so by the induction hypothesis, since x prime is smaller than x, because x is the successor of x prime, I should know this, right? So from this, and then I get given two cases. Either I'm in this case, or I'm in that case. But that's good, because if I'm in this case, well, then kind of working forwards rather than backwards, I can stick a successor on both of these and get this, right? So if I know that x prime is smaller than y prime, smaller or equal to, then it should remain the case that the successor of x prime is smaller or equal to the successor of y prime. So here, I'm going to go left, and here is the other way around, right? So y prime is less than or equal to x prime. So I should be able to go right. Okay, and then here, so here I've gone left, here I've gone right. We just taken the goal from these two branches. But now I know a way of showing that the successor of something is less than or equal to the successor of something. That's this rule here, right? Can you do that in both branches? And then because we have been given exactly the peeled off versions, then we just done here, right? So what did we do? Well, we had to do induction on something. Again, if I didn't do inductively x, then I wouldn't be entitled to this fact for the smaller things, and I would be stuck at this point, right? And then we were just looking at x and y. So we did a from x, and somewhere we did a from y. and just dealing with all the cases, right? So we're saying that, well, if x is 0, then we know we should go left here. If y is 0, then we know that we should go right, and so on. And otherwise, we do a recursive call, and we just keep the same case that we were in. So if this was a left, then we go left again. If this was a right, then we go right again. Right. Make sense?
I think so. No, people are nodding in the room. That's good.
That's good.
Okay, so if you stop sharing, then I will restart sharing. Let's where's the share button? There's the share button. Share away. Okay, so I of course should have been typing all that in as we went. So yes, you certainly get, yep. Which one? The one that Fred just did, or the one that I just did? Fred, can you fling that across on Mattermost?
That's what I'm doing as we speak.
Cool.
Yeah.
Okay. So if I can copy and paste. Okay. So yeah. Yeah. Well, we figured out that X is a successor, but we still don't know whether, which means that X is big-ish, but we don't know how big. So we're trying to compare X and Y. We now, there's some possibility that Y is 0. Right. If Y is 0, then it's definitely the small one. And if Y is a successor, the jury's still out. So yeah, so Fred's looking at Y to find out whether Y is 0 or not. And then, so there's 3 cases in this proof. The case where we find X is 0 and we can immediately go left and use les. Then there's the case where Y is 0, in which case we can immediately go right and use les. And then there's the case where they are both successors. And what we do there is peel off a spud from each side and go recursively to find out which way around they are. So inductively, we find out which predecessor is the big one. And then when we put the spuds back, they're in the same order. So that's what's going on there. Okay. So what I'm going to try and do in the last 15 minutes is to write a program and prove that it's correct. So we've defined the relation that says when one number is less than or equal to another. And the fact that I can define a relation doesn't necessarily mean I know how to compute whether the relation is true. Well, here I'm going to show that we can compute whether the relation is true. So I've given myself a type of bits, O and I looking like 0 and 1, representing false and true, respectively. So we had that last semester. And I'm going to write a function which tests whether X is less than or equal to Y. And because it's semester 2 and we're all grown up, we are allowed to define infix operators made out of symbols. And this thing where you write an infix operator in a set of parentheses is a way of turning an infix operator into a prefix operator, or just like treating it like it's an ordinary name. So if I don't want to fill in both inputs, if I want to talk about the thing itself, I put it in parentheses. So I'm saying less than or equal is an operator which takes 2 numbers and gives you a bit. Okay, so I'm going to define it. It doesn't really matter whether I go inductively on X or on Y because they're both going to get smaller. I'm going to look at X. Because if X is already 0, whoops, sorry about that. Then I need look no further. I know the answer is true. If I know that X is already a successor, then I better learn about Y. Because Y might be 0. All right. So if the thing on the right is 0 and the thing on the left is a successor, then it's definitely false. And if we know that both things are successors, then we peel a spud off each side and we know we're balanced out. So that's testing X less than or equal to Y. Okay, so I have defined our function. It's a function that gives you a bit. But what bit? You know, what does this function giving back a true or false answer actually tell you about the numbers? It just tells you put some numbers into an input slot and a bit came out. There's no, I mean, we might talk to each other about what that bit means, but you know, it's a bit. You can use it anywhere a bit is expected, and it might not be appropriate. So let us actually prove what it means for this thing to return true. So what I'm going to prove is that if my function returns true, then that's the same, that's logically equivalent to our relation holding. So the test X less than or equal to Y returns true if and only if X is actually less than or equal to Y. Does that seem reasonable? Okay, let's do it. It's going to go, I mean, same game. Why is it stuck? I can say inductively X, and then I say from X, and I get a horrible X128, which I'm going to turn into X prime. Okay, but here, what have I got? I have to prove that these are equivalent statements, but I expect that knowing that the first input was 0 is actually going to get me some computation. And as of yesterday, you are now allowed to say test when the goal is something other than an equation. So test just means run this as much as you can. So we discover that we are actually trying to show that one boringly true statement, namely true equals true, is equivalent to another boringly true statement. So I think we've got some chance. Okay, and it didn't even ask for the way around in which true, it's just an equation that's already true. But it's saying, okay, given a not very exciting fact, show a not very exciting fact, I can do that by the 0 rule. Okay, one base case out of the way. Now, we know that next thing our function would like to know is about Y. So we're going to do from Y, and then I'm going to change X136 to Y prime. Okay. So again, we are expecting that we can do a little bit of computation. So I will say test. And now we're being asked to show the equivalence of one very, very false fact with another very, very false fact. And this time we do get two cases, but guess what, folks? All you have to do is poke a bit hard at them, right? We've got an equational hypothesis that two things which are blatantly different are equal. So if we say, essentially, this is saying, I don't believe you. Yes. Or how could that be true? And then likewise, we ask, how could this be true? And you know what? It isn't. So we've got our other base case. So next up, what happens? I'm going to say test again, because I think I'm going to get some computation. And oh, look, I've got something I quite like the look of. Yeah, actually, there's some interesting ways I could prove this, but I'm going to do it the stupid way. Yeah, so I've still got double successors, but I know I can do something about on the relational side, but I know I can do something about that. These are reassuringly nice and small. So I'm going to go by equivalence. And now I'm being given one way then the other. Here I go by the double successor rule, and now I'm in good shape. So because I know, now here's the thing I have to do. I know that I've got an equivalence only with primes on. And I want to show that the left-hand side implies the right-hand side. And remember, a moment ago, we proved that. For things called A and B, but now we get to use that information for something more specific than A and B. You can see it's quite happy to accept that we know that. And it says, well, in that case, prove the two conditions. And I do that by and introduction. And one of them is given inductively, and one of them was sitting right there. Okay, so this thing here is the induction hypothesis, and this is the thing we were given in the equivalence. And then the same deal happens here, only this time we have to strip off the double successor on the given, but that's okay. And we're going to make the same move. I'm just going to grab that line and swap around what's here. And again, it accepts that that implication is okay because we proved it earlier for general purpose A and B. And now I've got two things to prove, and I'll split them up using and introduction. And they're both true. One of them's the induction hypothesis, and the other one is the assumption that I was just given. So there we are, folks. We introduced a notion of logical equivalence, and we have used it to show the equivalence of a logical notion of less than or equals between two numbers. and a practical computational way of testing whether whether one number is less than or equal to another. So in fact, it's might be nice to finish by saying, let's do another proof of actually successor of 0, 2 is less than or equal to, I'm just picking one that we didn't already do. 2 is less than or equal to 3. Right. And what am I going to do? I'm going to do that from, I'm going to make use of this fact. Ooh, if Zoom will let me pick it up and drop it. Copy that and put it there. And copy that and put it there. So I'm going to use the implication this way around. And now I'm going to substitute. Instead of x, I'm going to have 2. And instead of y, I'm going to have 3. Yep. So big old search and replace to do a substitution. And now what have I done wrong? Oh no, hang on, it's fine.
I think that's
I just
fine.
need to do and introduction.
Yeah.
And that's it. Right. Why did both sub-goals disappear? The left sub-goal disappeared because it's the thing we just proved, that equivalence, it's a special case of it, and ask lets you have special cases. And the other sub-goal is straightforwardly true because ask is willing to run the program. So the second sub-goal reduced to true equals true. So we also have learned an important trick that if we can show the equivalence of the outcome of a computation and some logical notion that we're interested in, we can tell the computer to do the bloody work. And there's nothing I love more than watching a computer do work that I'm not doing. Okay, folks, let's stop there. Thanks very much. Thank you, Fred. Get well soon.
I'll do my best.
Cheers.
Cheers.